to my talk, Building a Proprietary Rendering Engine. My name is Martin Sobek. I'm the lead rendering engineer at Hangar 13 at Brno. Hangar 13 is the author of Mafia III game, and we've got 4 locations around the world. One of them is in Novato in California. 2 of them are in Czech Republic, in Prague and Brno. And the good news is one of them is right here in Brighton. So let me do a quick recap of the history of this rendering engine. It was built from the scratch for Mafia II. It was basically at the time written by one genius guy, Petr Smilek. And at that time, this was targeted at PlayStation 3, Xbox 360, and PC. This was basically the DX9 generation. It was using the forward shading rendering pipeline, which basically is what everybody was doing. Low dynamic range, everything was single-threaded. We had fixed time of day. There was no time flow, no weather changes. So we didn't actually have any global illumination system in place. And we just used baked ambient occlusion to achieve something like a fake GI or something. Then for Mafia III, we significantly upgraded the engine. And I would say the biggest stress, except for having to port it to new platforms, to new generation, the biggest stress was put to dynamic gameplay. So first of all, we wanted a dynamic time of day. So the sun is moving on the sky. We have daytime, nighttime, but also dynamic weather, which is basically fully random, which is, in the end, maybe a bit tricky because sometimes the weather conditions just do not really look that great. But that was the main focus, make it fully dynamic. So because of that, we couldn't really bake almost anything. Everything is real time, and that brought us quite a lot of challenges. This was DX11 generation hardware, so PlayStation 4, Xbox One, and later on we added a patch for the upgraded versions of these two. It was multi-threaded, like heavily multi-threaded. We switched to physically based shaders, high dynamic range. We used Blink-Fong shading model, and I would say the biggest or the most unique 2 things that I could mention on that is first of all a unique shader system. I would call it inheritance-based shader system. And actually there was a GDC talk by Bungie on GDC 2018, I think, and they have pretty much similar thing as we do. I haven't seen that anywhere else yet. And it is basically a node-based shader system, but what we call nodes, it's not really the actual operands or the operations, just like you know from Unreal or other engines. But by nodes, we mean certain values or certain, like named semantic parameters. Like for example, the normal would be a node. And like how we compute it, that's not, the equation is not what we call node. And then you can basically override your shader. You can create a new shader, and you say, I'm actually defining this shader from another parent shader, and I'm just changing the normal because I want to add like a second normal map layer. So this is how it works. And the second unique thing is our ray trace reflections, to be more correct, ray march reflections. I had a separate GDC talk last year on GDC last year, and this was just about that. So I'll not go into too much details on that topic, but I'll just mention that we use that for real-time reflections. And what we have added since Mafia III, it's still the same engine. We have evolved it a bit. There are no like major changes. We have switched to GGX, which is now the industry standard. Everybody is using that. And we have extended the ray march reflections. Now we also use it for global illumination. But this is now under heavy development, so I don't want to dig too much into the details. Maybe next year when this is more polished, I'll probably disclose how that works. Then we added a new virtual texturing system, which I think is also something that now many teams are adopting, and GPU particle simulation. This one was heavily inspired, again, by Bungie, so it looks like there is a small bridge between the 2 studios, even though we haven't really spoken to any of them, but we're doing something very similar. So now let's have a look at the actual frame rendering breakdown. We represent the scene as hierarchical spatial hash, so there are multiple levels of different sizes. Each upper level is double the size of the low level. And we have 2 subdivisions. It's all based on pre-computed ABB. one for static and one for dynamic. The reason for that is basically because it's an open world, we are streaming a lot. Basically every time, especially when the player is driving a car, which can be like 100 miles per hour, you have to basically constantly stream something in and something out. So the scene is changing constantly. So we needed something very optimal, and the spatial hash actually seems to work pretty fine. For visibility, we use GPU occlusion queries, and we use latent occlusion queries because otherwise we would have to wait for the results from the current frame and block the GPU. That wouldn't be efficient. This brings certain challenges because you are using data from the previous frame and assume what is visible and what not based on the results from the previous frames. But for third-person game, that seems to be quite fine. And also, this is a 30 FPS game on consoles. So as I said, we moved from forward shading pipeline on Mafia II to deferred shading pipeline on Mafia III. So what that means, at first, we just render the scene into frame buffers which contain the material information, what we called gbuffer. Just a quick refresher about GPU rasterization. That works in batches. And one batch is typically one material, but doesn't have to be like that. And for each batch, you just set up all the inputs that the shader needs, bind the render targets, and then submit that draw call into GPU. This is all happening on the CPU. You have a command buffer for the GPU, and in our case, this command buffer is typically executed or picked up by the GPU about one frame later. We actually have a limit, so you can't exceed that one frame, because we always want to get the data from the occlusion culling from the previous frame, so there's a hard limit. We don't buffer more than just one frame. So what is that, what we define, what do we call material? We have some fixed parameters. All materials have the same fixed parameters. So this is basically a bond to the shader, which shader is associated with that material. We have some basic behavior. Is it opaque, alpha blended, alpha added? Is it two-sided, and stuff like that. And then we have shader parameters. These are generated by the shader system, and based on what inputs you use in your shader, it will add all these inputs into the UI of that material. So this is dynamic, and is populated once you just pick the shader, the UI is populated. So the inputs are typically textures, some user values, and colors, and stuff like that. So how do we generate the batches? We first process all primarily visible objects. So these are the objects which have been gotten from the visibility system. Okay, these objects are supposed to be visible. And instead of submitting one object after another, we just break these up into the actual batches. We call them render elements. And so an object then have multiple materials. It can even be tens of materials, let's say on a building. So we just generate a render element for each of these materials or phase groups or whatever we want to call that. And we have two types of these, or two queues, I would say. One is for opaque, that goes to the gbuffer rendering, and then we have another for transparent, which is processed separate. And we have two types of these elements. One is the actual elements with the actual materials that the artists have chosen. And then we have so-called collapsed render elements. And these are used for rendering shadow maps or Z-prepass and stuff like that, where the material just doesn't matter at all. I mean, there are also some exceptions, because if you have alpha keyed material or alpha blended, then it actually matters what materials you have chosen. But on most draw calls, it doesn't matter, so we just fall back to a simple material, and then we can render the entire object as one draw call instead of like splitting it to 10 draw calls or something. Then once we have the render elements, so the broken down objects, we sort them, and there are two reasons for sorting them. Actually, the visual result doesn't matter. I mean, there is no change. You change the order, and the visual result is always the same. But the reasons are, it's two performance reasons. So one of them is you want to reduce the CPU overhead of submitting the draw calls. So you want to sort them in a way that the state changes between two draw calls are minimal. So you want to sort them so that most of them have the same shader, then that they have the same material, and index and vertex buffer. So imagine in this room, it would probably render maybe all of these chairs, but only the red part of it. The golden part would be a different material. So then all the chairs, the golden part of the chairs. The sort function, well, actually, another reason for that is GPU overdraw. So we want to kind of render that front to back. But like these are in direct contradiction. So if you saw them front to back, you'll most likely break the order of having efficient state switching. So we kind of came to the conclusion that we will have like a hybrid sort. So the first criteria is we assign the objects into a distance bin, and we have 3 of them. The first one is up to 10 meters, then from 10 to 50 meters, and then what is behind 50 meters. And within these bins, we sort that by shader, material, and index vertex buffer. We have an optional Z prepass, which in fact still seems to be valuable in most cases. So what that means, we just render not all the objects that go into the G buffer, but we have a heuristic function that tells it, is that actually worth rendering into Z prepass or not? The Z prepass is just an optimization. It again doesn't have any visual impact. And so the objects which are big on the screen and also are quite close to the camera are good candidates for Z prepass, so just render them using that simplified shaders. And then the G buffer rendering is actually faster because the early Z is working much better. So this adds some CPU overhead, also a little bit of GPU overhead. I think in our case it was approximately 0.5 milliseconds on the GPU. But typically we saved something like 1.5 or 2 milliseconds on the GPU, so it was definitely worth it in most cases. So as I said, this is a deferred shading pipeline. So if you can read that, which is not that important, but basically we have up to 6 render targets. The last one is optional. Mainly it's like the albedo, normals. There are some metadata. This one is very important. Velocity buffer. So we have per pixel velocity information, which tells it what are the UVs of that pixel in the previous frame. We use that very often, not only for the actual temporal anti-aliasing and motion blur, but we use that in many other effects like SSAO, reflections, and just to get the most out of the results from the previous frames. Just an example of a few of the render targets. And once we have the G buffer filled up, then we can apply lighting. In typical scene, I think it was like 5.5 milliseconds on the G buffer to like 7 milliseconds. So that's the actual scene rendering. From now on, we basically do not get back to the objects anymore because all of the data that we need are written in the G buffer. So the scene rendering has been finished, and now we're going for lighting. We support multiple light types. All of these light types are dynamic. There is no light baking. So there is one global light. This is typically the sun or moon, affecting the entire scene. And the shadows of this light are pretty much very complicated. There are multiple systems. There's no silver bullet. So what do we use? So the shadows that are updated every frame, and the highest quality is per object shadow maps. On Mafia 3, I think it was only the player and maybe the player's car was using that per object shadow maps. This is really a shadow map just allocated for one object, and this was typically very high resolution, also depending on the size of the object on the screen. Then still updated every frame, PSSMs, parallel split shadow maps. These were up to 50 meters, and these were, again, all of them rendered every single frame. We rendered both static and dynamic objects in them, and we used 2 cascades on consoles and up to 3 cascades on PC. And then we have 2 types of cached shadow maps, and these are up to 800 meters. And this is only for static objects. These are updated once the camera moves by a certain threshold or when the sun angle changes by a certain threshold. And because we use temporal anti-aliasing, we can hide the artifact of the shadows popping when the angle is changing. And we recently added something that is new. I mean, the technique is not new, but we added it. Height field shadows. This is a very simple trick. You just have even pre-rendered, or you render that at low time or something, the height field, so from the top. And then for each sun direction, you can pre-compute what would be the threshold height where you go from light to shadow, which is actually a very simple trick. And then using it, fetching it is very fast. You can have really long shadows from distant geometry, like distant buildings and distant terrain and that stuff. Because in Mafia 3, we're quite struggling with that. When the sun was almost on the horizon, you'd basically have to render the entire city into the shadow map, because like even a distant building can cast shadows on the place where you are. So this was very performance heavy. And we, in fact, did a cheat. We clamped the sun, just the sun angle for the shadows, so then it was not really matching. Like the sun would go down to the horizon, but the shadows would be clamped. I think it was like 20 degrees. So we definitely wanted to do better, and this works pretty nice. Then we have the classic light types: point lights, spotlights, and directional lights. Spotlights and point lights are the ones used most. On point lights, we cheat a bit, so we only allow shadows in basically just like for spotlights, so in a certain cone or pyramid. The rest is not shadowed. Just a refresher of shadow maps: you render the scene from the point of view of the light, you render the depth into that, and then you compare if the depth of the point that you want to shade is smaller or bigger than that. It is either on sun, on the light, or in the shade. And now I'll describe a bit how I do the actual shading. So we split the shading type into 4 different classes. It's 2x2 matrix, basically. The first one, classification, is it direct or indirect? What I mean by direct is that the point is directly lit, directly visible from that from that light source. And indirect, this is some kind of bounce. So this is basically environment lighting. So that's the first classification. And the second is diffuse versus specular. Diffuse is just going all directions, and specular based on some specular lobe and is view dependent. And while diffuse is only for non-metallic, specular is everywhere, and the parameters that drive it are roughness, reflectance, and reflectivity. And so these are the solutions to the actual light or shading types. So for diffuse, we use just Lambert and Odell. For specular, we use GGX. And then for the indirect, this is all in-house. This is the specific to our engine. We use something we call GI system and reflection system. And I'll just talk a little bit more about them, but not too much. And this is an example of one screenshot breakdown. So on the left, we've got the direct shading. On the right, the indirect shading. So this is all coming from rematching, and the result is just the sum of all of these together. So for the direct accumulation, we basically render the light volume, so the 3D volumes of the lights, which is for the point lights, it's a sphere. For the spotlight, it's a cone. And we only do a little trick. We just flip the z-test so that instead of using less than or less or equal, we use greater than. So that means if the volume is somewhere in front of the wall, nothing is being processed, no pixel shade is running. But when it hits the wall and penetrates into the wall, those are the pixels which are then being processed on the GPU. And then you could say, okay, but this way you would render light which is even far away behind the wall. Actually, no, because the occlusion system would find out that this entire light is occluded and would not be processed. So this one is quite efficient. Where it starts to lose a bit is in the distance, where you have basically many lights overlapping the same area. And for these, we actually used screen space projected quads. And this is just a little bit more efficient, but pretty much doing the same thing. So for each of the visible lights, you can allocate a shadow map based on the size of the light, based on some user parameters, quality of your shadow maps, how far that is. And then in the pixel shader, you compute the direct shading, and output that, we use just additive blending to accumulate all the lights. That's just very simple. And then we just add the results of the indirect, and that's it. We've got the final shading. So now I'll just very quickly describe the reflections and GI. Basically, you would find that on GDC Vault from last year. There's more information, but only on the reflection. So how it works, artists place reflection probes somewhere in the scene. This would be still pretty much the same that everybody is doing, but we render also the depth for these cube maps, and then instead of just doing a cube map lookup, we rematch these cube maps and have basically parallax corrected results everywhere. Also, we can't really pre-render these because everything is changing in the game. Time of day is passing, weather is changing, the player can influence with the world, so he can just shoot some lights or something, or put some obstacle somewhere. So these are just rendered at runtime. Once we detect that we need to update the cube maps, they are re-rendered. And we shoot one ray per pixel at half res and then upscale. So there is quite a lot of tricks happening there, like temporal filtering, map mapping, and all that stuff to avoid all that noise artifacts. Because that's the biggest issue, right? You can shoot one ray, but then you will have quite a lot of noise, so you need to get rid of that. So most of the talk is actually just about like removal of the noise. These are the two examples. On the left, we see reflections. On the right, the GI buffer for the same shot. In fact, it's just one system. Most of the shaders are the same, but there's just different configuration. So different configuration for like what is the distribution of the rays, and different configuration for how we eliminate the noise. The biggest difference is like reflections are view dependent. So once the camera moves sideways, this is very tricky to resolve. For GI, it doesn't matter, so this is much more aggressive. But on the other hand, on GI, you have rays going everywhere, so you have much more noise. So they kind of interfere with each other. Volumetric effects, so something like that. This is using a 3D texture, which is projected or placed with the camera frustum. So there is 64 slices. And the good thing about this is all the samples are on the screen, so you don't waste any single sample. And they are placed quite perfectly. But on the other hand, a big disadvantage of that distribution is that when the camera moves, you see quite a lot of aliasing, like temporal aliasing. So right now we are redesigning this a bit. We are placing the slices in a different way. So basically for each pixel on the screen, we try to pre-compute like what is the best distribution of the samples in the Z direction. And that seems to give much better results. But this is, again, not finished yet, work in progress. So that was the setup for Mafia 3. This was 192 by 128, 64 slices. I mean, if you count that together, this is still 2 megapixels, so you can't really go too much crazy with that. It still has to be very simple. And the view distance was limited to 300 meters. I mean, if extended to the camera distance, those 64 slices was just by far not enough. I would say even the 300 meters was quite a lot. So at each of these points in space, you compute like what is, you accumulate the lighting at that point, but it's not very directional. So we compute like what is the light flux, let's say, going through that point. And then we also accumulate the direction to the light, weight it with the luminance of it. So what we get in the end is like, I would say, important light direction, something like average, weighted average light direction, and we use that to then do a fake speculus on glass and that stuff. I mean, it is not great, but given the fact that this reduces the cost dramatically, I quite like the effect, and I think we'll just stick to it. Alpha blended and force forward. So not all the objects can be rendered using the shading pipeline. The typical example is alpha blended transparent objects. At first, we just used a fallback to go to the forward shading pipeline. But because when you're using forward shading pipeline, you will have probably quite a lot of shader combinations because, I mean, at that time, we still didn't do dynamic loops in the shaders when we switched to the deferred shading. So now you could probably like do a dynamic loop and have like texture array with the shadow maps. That would be probably better. But at that time, we didn't want to do that. So on Mafia 3, we had basically many combinations for each shader, depending on how many lights were influencing that shader and what light types. So it could be like hundreds of combinations for each shader. We didn't want to do that, so we basically just had one light per pass. And what could happen is typically in cinematics that people place a glass and they put like 10 lights. Suddenly the glass was rendered 10 times and everything was super slow. So then we implemented that volumetric rendering and the approximation using the major light direction. The forward shading pipeline is still in place. It can be used whenever you know that there is only, let's say, one light influencing that. So this is used sometimes in cinematics when they want to have like really high quality. But in general, this is not something that we invested a lot of time into, and I think it might still need some improvements. So alpha blended are accumulated front to back, back to front. And the problem is we always sort it based on the object distance, but do not sort triangles within the object. So artists still are struggling with that. I don't have any good solution for that. I'm thinking about maybe having different variations of the index buffer based on the view direction of it, and then dynamically choose which one to use. Maybe that, we'll see. I mean, we didn't want to use the auto-independent transparency. I don't know from what year that is. I don't think anybody is using that in production because this is really unpredictable. If you have like the glass like really close to the camera, you would need 5 times more memory and that stuff. So we'll see. And post effects. These are basically effects that are attached to the camera. So this is like a quad that is rendered at the entire screen. This is fully artist controlled, so artists really create the stack. They set the order of these operations. And the typical shaders that we use all the time are tone mapping. We go from HDR to LDR, bloom, color grading, depth of field, motion blur, vignetting and camera distortion, typically in cinematics, and chromatic aberration as well, cinematics mainly. We only have one optimization there. So at the end, or just before shipping the game, we just looked at what are the actual combinations that are being used, because some of them are really trivial. So we're heavily underutilizing the shader cores. So what we did is just we put together into one shader the shader chains that we're just using most. And then if we see that this is the combination that we have actually manually baked in, we just use that one. And that was saving like maybe 0.5 milliseconds on the GPU. I have not really covered these things. I mean, each of them would be maybe for a small talk separate to this. I have used some images from the internet rather than drawing them myself. And basically that concludes the talk. What are the questions?
Hey, when it comes to storing depth in the cube maps, how do you handle things like occlusions within the cube maps themselves, and then the ray march not being able to find a good solution to that?
We didn't. I mean, at first, I thought it would store multiple depths. Actually, there was an article in, I think, GPU James 3, where they actually do it. Like they call it layered cube maps. But in the end, I decided not to do that. And what actually works pretty nice for us is you place multiple of these cube maps. We have a debug for the artist, and I can show you that. It's this one. Each of these colors is a color code of these cube maps. So the artists, when placing the cube maps, they see which areas are already covered by some cube map and which not. So they want to minimize. You might see like black and white strips somewhere, maybe. Actually, not many of them, so which is a good sign. I mean, yeah, there are a few here, for example. So that means there is no cube map that has a visibility to that place. But we also use screen space. So quite a lot of it is covered by the screen space. As a fallback, you have a set of cube maps, which actually cover 90% of the environment. And only where both of them are failing, we are missing reflections. And the places where this was happening is just so minimal. And it's in artist's hand to actually place the cube maps in such a way, using that debug so that it works fine. Because we don't remarch just one cube map, but when we actually hit that region where the visibility is occluded, we actually look up which other cube map can pick it up from there. So basically, if you have like columns in this room or whatever, let's say I'm tracing from here, I hit the place behind the column, there will be another cube map maybe on the other side of the room, picks it up and continues. I mean, on Mafia 3, it was a little bit, I would say, trivial implementation, so that it was basically checking all other cube maps if they have visibility, like up to 4 of them, not all cube maps. And now we have an improved version. So we have a 3D texture, very low res. I think the base resolution is 1 meter, and it's like 60 meters radius from the camera. And in that cell, we store what is the best cube map for that voxel. So then we just look it up from there and go and trace that cube map, rematch that cube map, which is the best fit for that place. There was also one question there.
This isn't a low-level question, but it was how many people do you have working on the engine and the tools, on this engine and the tools?
On the engine in general, you mean like everything, like platforms, render,
supporting the fact
tools.
that you're making your own tech rather than using other people's tech.
We've got the game technical director here. Maybe he knows better. I think it's around like 40 to 50 people on the engine.
Maybe on the engine itself, like glass, then we have people on game.
True. Yeah. So maybe like 30 on the engine.
Yeah.
Could be. I mean, the render itself, we've got 2 guys in Novato, California. We've got 6 guys in Brno. And then we have guys which are like so working like on the render, but more on the pipeline side. Yeah, I would say, yeah, about 30 people probably.
Is it ever tempting to think that those 30 people could be?
Sorry.
Is it ever tempting to think that those 30 people could be making the games if you used like Unreal or Unity or something?
Oh yeah, that's a question that we have discussed many times in the past. I mean, it might have changed. I mean, all the engines are evolving. Even Unreal is evolving quite heavily. I mean, they have really lots of engineers. But at the time where it was still, let's say, possible to switch to Unreal when talking about Mafia III, Unreal didn't support any streaming whatsoever. So for an open world game, this was basically a very easy answer. Like, there was no engine that would support it at that time. And I mean, as far as I know, I don't think that they have it even now. Like, that Unreal Engine is suitable for open world. I mean, I think the Batman was probably the biggest open world game on Unreal. But what I have read, it looks like they did like heavy modifications to the engine. So then it's like, what's the cost? Like doing the modifications of a third-party engine or actually writing our own.
So the open world was the main reason why you didn't use?
Yeah. Mm-hmm. And also like the dynamicity of the environment. I mean, in Unreal, again, a long time ago, there was involved quite a lot of baking. Basically, the lighting, most of the lighting was baked, and you couldn't do too much real-time lighting. At that time, it was still forward, actually, at that time. Then they switched to deferred, so I guess now it's much better. I assume that, again, like if we decide now for Mafia 3, that might be slightly different, but at that time the arguments were quite strong.
Thank you.
Yeah, but also like from my point of view, I think that for AAA game development, it's just much better to maintain your own, because you are not dependent so much on what other people are doing, and you have full control over it.
With just 30 people making the engine.
Yeah, right. Yeah, but I have to say that I mean at Hangar 13, it looks like we have quite I would say quite free hands. I have spoken to other developments from like different teams, and it looks like if you want to do something crazy, and basically the reflections, that was quite a lot crazy. I mean, I didn't think I would spend that much time on it. It was like 1 year altogether, maybe. So if I had known that before, I'm not sure if I would decide to go for that. But the estimates were just much more optimistic, right? I was like, yeah, I mean, I have an idea. It worked on my prototype. The prototype was done in 3 days. Works perfect. So I assume 3 months. It was 1 year. And then another like few months after Mafia 3 to improve it to the current state. But in Hangar 13, and I would say in 2K in general, we have the opportunity to do that kind of research, and basically it's mainly the leads doing the decision. The directors, most of the time, as far as I can tell, just give them quite a lot of freedom. So that's really cool.
You mentioned The Z prepass uses a heuristic based on profiling. Does that run offline on every object in the world?
No, I'm sorry. The heuristic was basically manually tweaking the values. So I think the main one, we basically assign a score to each draw call, and the main contributors are the size of the object on the screen. So we basically take the ABB, project it on a rectangle on the screen. So there is a threshold for that, and then also the distance. Because even if there's something really huge, like on the screen, it's like, I don't know, like a building somewhere in the back, it doesn't probably occlude anything. So it's the size and the distance. And I think it was about like 1 to 200 draw calls was a typical Z prepass. About the collapsed draw calls. So it's almost like 100 to 200 objects that have been picked for the Z prepass. Yeah, at first I was quite skeptical about the Z prepass because I said like it's just an overhead on the CPU and on the GPU. But because it's really a single material, all of that, except for alpha tested, it was a big win. And especially, like alpha tested, I said, no way that it's going to be faster with the Z prepass. I was so wrong. I mean, so basically, we force everything that is alpha tested goes into the Z prepass. And then in the gbuffer rendering, we use equal Z test and do not use alpha clipping. And then basically, because if you do alpha clipping, the early Z doesn't really work, and this helped it dramatically.
I guess somewhat similarly, for shadow rendering and Z prepass, do you kind of have a separate vertex buffer that has duplicated all of the vertex position data, so that you have one with all of the attributes and one with just positions?
No, we have always all attributes packed into one vertex buffer. So I mean, might be something to consider to actually split that to an optimized version for the shadow map rendering. What I have seen in the profilers, it looks like, I mean, it's not really documented really well, but it looks like it's not executing the vertex shaders on all the wavefronts. There are some limitations, so I don't know if that would actually help, but it's definitely something to try. In the back.
Excuse me. Hi, you talked about the optimization of the prepass. For like a common combination, is that literally kind of taking those modular shaders and collapsing them into a big hand-optimized version, or could you go into that a bit more, maybe?
Yeah, it's actually much simpler than that. Basically, the shader builder knows if there is any special vertex processing happening. So let's say trees have wind animation and that stuff. So basically, for the basic ones, or for the most common ones, which is standard projection, skinned projection, and single matrix skinning, whatever to call it, for these, we actually use basically null pixel shader and trivial vertex shader, which was just written once. And for anything else, we use the same vertex shader, and then pixel shader, it's depending only if it's alpha tested or not. So either use trivial or the actual one. And we just actually output like 0 but clip based on the alpha. So the shader compiler then strips everything that's not really needed. So the shaders are really optimal. And most of them are just handwritten, which is those like 3. And the ones that are not, the compiler, we just let the compiler know, hey, you are compiling for the depth pass, because you just strip out everything that we don't need, and the compiler does the rest.
Thank you.
All right. Thank you very much.